you see some people wearing masks because I just got recovered from COVID, and then today I heard from Linda that she got COVID positive today. So just in case, I think I'm recovered, but maybe some of you might. Anyway, I'm very pleased to have Tony Huynh, who is a new member of the Discrete Math Group. This is his first talk after becoming a member. Something about rainbow, right?
Yes.
Yeah, please.
This is true. Okay. Thanks, Daniel. So yeah, I mean it's nice to be back here forever now. Yeah, so this work actually started at IBS about a year ago at the mostly matroids workshop. So I'd like to thank the organizers of that workshop. And it actually started 1 week before that workshop at a pre-workshop meeting for graduate students. That was organized by Rutger, so I think he put in a lot of work and did a great job of having nice problems for the students. So so Dylan, Wayne are grad students, or were grad students at LSU when this started, and Matthew was a grad student at Waterloo at the time. Okay, so let me. Okay, this talk is about a geometric version of the Erdős-Hajnal conjecture. So probably everyone knows, but let me just start with the normal Erdős-Hajnal conjecture for graphs. So of course, like a big theme in graph theory is to understand the structure of graphs if you forbid, say, your favorite graph as an inductive graph. And maybe the most famous conjecture along these lines is the Erdős-Hajnal conjecture. So let me just state it, although probably everyone knows what it is. So this is an old conjecture of Erdős-Hajnal from 1977, and it says that for every graph H, so think of H as maybe a small graph that you want to forbid. So once you forbid H as an induced subgraph, something interesting happens, right? So for every graph H, there exists some epsilon, and this epsilon depends on H. So such that every H-free graph so here H-free just means you don't have H as a induced subgraph. So every H-free graph on, let's say, n vertices contains a clique or stable set that's large, right? So here large means it's polynomial in end, right? So of size at least n to the epsilon. Okay, right? So we know from Ramsey's theorem that every graph has a clique or a stable set of size log n. So this says that, okay, once you forbid I don't know, your favorite graph as an induced subgraph, you can expect to have much larger. So sometimes these are called homogeneous sets because either all the edges are there or none of the edges are there. Right. Okay, so this is still open. I should say there's a lot of, I mean, this is a very active area. There's a lot of nice results. So maybe check out the survey article by Maria Chudnovsky if you want to learn more about conjecture. I want to stress maybe that not a lot is known about Erdős-Hajnal in the sense that we know that it's only true for some graphs. So the h's for which we know it's true is pretty small. So there's lots of partial results where you can forbid more than one graph. You can maybe try to prove a bound that's not quite as good as this, right? But here for this talk, I want to stress that okay, kind of little is known. So move this up. Let's put this here. So known cases. Let's do it like this. So it is known to be true when H is a cograph. So as far as I know, this is basically essentially like the only infinite class of graph for which conjecture is known. So a cograph is just a graph that doesn't have an induced path with 3 edges. Right? They have lots of nice properties, lots of other nice characterizations. Okay, and then it's true if H is small. So if say H has less than 4 vertices, and then things already get quite hard when H has 5 vertices, right? So it's also true when H is the bowl graph. So the bowl is the graph that looks like a bowl, right? So this thing. So this is already quite a hard theorem of Chernowski and Safra. This is from 08. And then it's also known to be true when H is the 5 cycle. So this is a recent theorem of Chernowski, Scott, Seymour, Sparkle. So this is quite interesting because, right, so for this H, it's known that something called the strong Erdős-Hajnal property does not hold, right? So they really needed some new techniques to prove it for the 5 cycle. And then most recently, it's also true for the 5 vertex path. So this is, as far as I know, this is not published yet, so this is a theorem of Scott and Seymour. This is, I'll just write this as 25 plus. And okay, from known results, this implies that it's true for all 5 vertex graphs, actually. Okay. So we know that it's true for all graphs with at most 5 vertices, and for cographs, it's essentially all that's known. Okay. Okay, so for this talk, we want to make the problem even harder. So we'll make it harder, I guess, in 2 ways. Like one is we're going to introduce colors. So we're going to introduce like the colored version. And then we're going to do it for matroids or representable matroids instead of for graphs. So we'll generalize in 2 different directions. So let me first tell you about like the let's do the colors first. So let me first tell you the multicolored Erdős-Hajnal conjecture. Okay. Okay. So maybe I need to tell you. Okay, we need some definitions of like what it means for one colored graph to contain another colored graph. Okay, so when we move to the colored version, we only need to consider colorings of complete graphs, right? So let's let C and D colorings.
of complete graphs. H and G. So in this talk, colorings always mean I color the edges of the graph, not the vertices of the graph, right? And now I have to tell you what it means for like one colored clique to contain like another colored clique, right? So, we say it is probably what you think, right? We say D contains C. Right, so if there is an injection let's call this phi from the vertices of H, so H is the smaller graph, to the vertices of G, such that the color of every edge is actually what you expect. So D of phi of x, phi of y. Right. So this is for all distinct vertices x, y. Okay, so I wrote that down just to be precise, but it's not really that complicated. So say I have a colored clique, maybe it's something like this. Red, 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 red. So this contains like a red triangle. So for example, right, because this red triangle is just like right here, right? Okay, so I hope that's clear. And then it will be convenient to like fix the set of colors to be like the numbers from like 1 to S, let's say, right? So so an S coloring is coloring, let's see, with codomain S. I'll also use this notation. Okay, so now I can state this multicolored Erdős-Hajnal conjecture. So this is actually a conjecture that was made by Erdős-Hajnal as well. So a bit later. So so this is the multicolored Erdős-Hajnal conjecture. I think this is from '89. So we'll see that this implies the normal Erdős-Hajnal conjecture. So it just says that so for all, so this S naught is going to be the number of colors used in the coloring of like the smaller graph, and this S is going to be like the number of colors that's used in the coloring of like the ambient, like larger graph. So this is K, and every S0 coloring, let's say C0 of a complete graph on K vertices, so a KK here. There exists let's say delta and a c. So it'll be useful to have the c because sometimes like we can get exact results on the constant in front of the n to the delta, right? So if you don't care about the c, it's fine. Such that, right, so for every, so C0 free coloring. So C0 free just means you do not contain C0, like in the sense here, of Kn. There exists
Do you want S coloring of Kn?
yeah, so that's C0 free S coloring. Yeah, let's put that in. Right, so the conclusion should be that there is some large set of vertices that avoids some color, right? So that's what it says. So there exists a color. There exists color. Let's say I in S, and some subset of vertices where this color I is missing amongst the edges in X, right? Such that the color of E is not I for all edges. With both ends. In X, right? So there's some, and of course this X is large. And the size of X is at least C times n to the delta, right? So it's polynomially large. So I'll also call like such an X like a homogeneous set, right? So homogeneous just means there is some color that is missing. Okay. What should I do? Maybe I'll just slide. You can write down here.
You can move the second one bottom and then.
Yeah, maybe I'll just write
Yeah.
here for now. Okay, so let me at least say that this multicolored version implies like the normal version just by taking two colors, right? So if you just have two colors and you sort of let like red be a non-edge and blue be an edge, then, well, like if you're missing a color and you only have two colors, you're actually monochromatic, right? So, so the two-colored version implies the normal version. Okay. Okay. So this is like not our conjecture. This is the conjecture of Erdős-Hajnal, but the colored version makes it kind of easy to generalize to matroids, right? Because now like we just have to like think about like the correspondence, right? That we should use, right? So, so what is a complete graph? Well, okay, so it's a graph that contains sort of every graph, right? So every graph or simple graph, let's say, is a subgraph of a big enough clique, right? That's sort of the property that that cliques have. So if we want the geometric version, like a clique corresponds to like a projective geometry, right? So okay, everyone should know what a matroid is, but if you don't, I will tell you. So you don't need to know a lot of matroid theory to follow this talk. Okay, so maybe this thing. It's not so important.
One at the bottom, all the way down.
Put it to the bottom.
Yeah, behind the space.
Like this.
Yeah.
This seems good. This seems good. Okay, so so now that we have this, oh, what happened to my? Oh yes, okay. So we have the multicolored Erdős-Hajnal for graphs, and now it should be straightforward to translate this into matroidal language, what the conjecture should be. So so as I said, complete graphs. These correspond to projective geometries. These are kind of like the universal objects for representable matroids, right? So the complete graphs contain kind of all the graphs under the subgraph relation. The projective geometries contain all the simple matroids, right? Oh, I should say that, right, so amongst the set of authors, I think Peter Nelson definitely knows the most about this topic, so there's a chance I'm going to say something completely wrong, and if that's the case, I apologize. Yeah, so, okay. So what is a projective geometry? So it's denoted as, so, okay, for this talk, we're really only going to consider projective geometries over finite fields. So we denote these as PG and minus 1Q. And these are basically the one-dimensional subspaces of GFQ to the n, right? So Q is a prime power. I look at the finite field of that order. I take n tuples, and then my points are the one-dimensional subspaces. Okay, if that's too complicated, it won't really hurt to think of just Q equals 2 for this talk, right? So, so let's say for this talk, Q equals 2, so we're really just talking about binary matroids. And then, well, you cannot really scale when Q equals 2, so this PG n minus 1, 2, this is just equal to all non-zero vectors. The binary field, n tuples of the binary field, right? So maybe, no, let me keep up this. Maybe I'll start erasing things. Let's erase this. Yeah, so for example, I guess this PG 2 is just like, well, you can think of it as just a set of vectors, maybe like this, all the non-zero vectors. So it has 7 points, and then sometimes we just draw it geometrically, right, as the found point. So this is also equal to maybe so these lines mean like these 3 points are literally dependent, right? So this is the same as this, right? Okay, so that's good. Let's continue the correspondence. So colorings. So remember we colored the edges of the complete graph. So colorings of the edges, these correspond to colorings of just the points in this projective geometry. So okay, and then homogeneous will just mean the same thing, right? So so homogeneous X. Remember, this is a subset of vertices. So this meaning is basically the same. We just have like a color that's missing. So this is a set of vertices. This will correspond to like the homogeneous subspace. So this is just a lower dimensional projective geometry. Space X of GG. Right, and then remember in Erdős-Hajnal, like what is large is like the number of vertices in this homogeneous set. So we have to translate the number of vertices to the matroidal language. That should be the dimension of this subspace, right? So, so the size of X here corresponds to the dimension of X here. Okay. Okay, so with these translations, well, you know what the conjecture should say, but maybe I'll just write it out to be precise. Maybe write it here.
There's one more word, something.
Oh, maybe.
Yeah.
Okay, yeah.
Right.
It should work. It should work. So this is our conjecture. This is a multicolored Erdős-Hajnal conjecture. Or so let's say for projective geometries. Okay, let me just write it out just so that it's clear what it is. But it should be clear what it is from just the correspondence I set up over there, right? So for every prime power Q all K, so K is going to be like the dimension of the projective geometry that I forbid. I have an S0, which is going to be the number of colors I use on this small projective geometry. I'm going to have an S, which is like the number of colors that I use in the large ambient projective geometry. So that means that S0 is at most S. And every S0 coloring, C0 of, so PG K minus 1Q. So there exists, so again, delta and C, you might not care what the C is, but it's fine. Such that, okay, so for all n, so n is going to be the dimension of the large projective geometry, and every C0 free S coloring, C of, so G is going to be projective geometry of dimension n. There should be some large subspace that avoids some color, right? So there is I'm going a lot slower than I anticipated, but we'll see. Subspace of G with dimension at least C times n to this delta, right? So it's polynomial in n. Okay, so again, like just as in for graphs, like the two-colored version says something about induced subgraphs. The two-colored version here says something about induced restrictions. So if you're interested in induced restrictions of matroids, so two colors sort of corresponds to induced restrictions. Let me erase this thing.
If you don't say polynomial, like into delta, then this must be known, right? Some Ramsey thing.
Something, yeah, should be. Yeah, there is like Ramsey theory for projective geometries where if you color the points of a projective geometry and you want some fixed projective geometry, yeah, this will be known, but certainly not with this n to the delta. But so I guess Peter spoke about this in Oberwolfach, and I guess when he did, Jacob Fox suggested that this might even hold with a linear function. So, so this is a bold. Let me just write this as bold conjecture. Well, I don't know if Jacob wants his name connected to this, but he was the one that suggested that it might actually hold with delta
You get
equals
to
1.
decide, right?
Yeah. Right, so one can take delta equals 1 above. Right, so this seems quite strong, but we don't know of any examples that refute this, right? So, so it could even hold with a linear function in n. Okay. Okay. Let me continue my mission. So, okay. So I guess for the remainder of the talk, which is maybe not that long, I want to prove our conjecture for some small projective geometries. So you might not be that impressed by that, but remember that for Erdős-Hajnal, it's basically also only known. Yeah, go ahead.
So related to the stronger version, can you, assuming this projective geometry conjecture, would you get something for the graph Erdős-Hajnal? Like
I think they're
the
kind
bonds
of.
work?
I think they're kind of incomparable, but sometimes I think things are nicer in the projective geometry world. So I'm not sure I'll get to it, but sometimes like the proofs are actually a bit cleaner for the projective geometries than for graphs. I think they're kind of incomparable. You can think of like if you just restrict to I guess sort of graphic matroids, then it becomes the same thing. So this is sort of harder, but not really. So yeah, I think they're incomparable. Okay, so I guess for the remainder of the talk, I'm gonna prove the theorem at least in the case that that K is small, basically just a triangle. So this will give some evidence that the conjecture is true, right? So okay, so maybe. So for the remainder of the talk, let's take Q is equal to 2. So we'll only consider basically binary matroids, and this K is equal to 3, right? So the dimension of the projective geometry I want to forbid is just 3, so it's just a triangle, right? So this means that what I'm forbidding is a triangle. But remember, this is a colored version, so there's like 3 different triangles that you could actually forbid. So there are like 3 cases. So okay, let's go to the colored chalk. Yellow maybe? Yellow, green, red. So so there's the case that the coloring is rainbow. So let's say maybe green. Oh, maybe yellow looks like green. Should I use blue? What is better? Maybe purple. Purple looks different than green, I guess, right? And red. So this is one case. I guess another case is the monochromatic case. So where points are the same color. So a triangle I'm just drawing as a line like this. And then there's another case where, yeah, like 2 of the colors are the same, and the third is like a different color. Okay, so let's start with the rainbow case, because I think it's quite nice. And in fact, okay, let's go back to graphs even, right? Let's make things maybe even easier for ourselves. So I want to solve this let's say this multicolored Erdős-Hajnal for like rainbow triangles, right? And in this case, I'm only going to do it when S is also equal to 3, so that the number of colors of the complete graph is also 3. Okay, so the way that we do it is sort of inspired from the graph version. So the way to do the graph version is to prove like a stronger theorem, right? So so it turns out that there's a structure theorem for like all rainbow triangle free colorings of complete graphs. So we know what they are. So question, what are the colorings? So remember, colorings always means the edges of the complete graph of Kn with no rainbow triangle. And it turns out that there's a beautiful theorem of Gallai that answers this question. So there's a characterization of all of these colorings. Right? So let me just write this. Right, this is Gallai's theorem. Okay, so every such coloring looks like, okay, so you can construct all of these colorings in the following way. So you partition the vertices of your complete graph into, let's say, V1, V2, up to Vt. Okay? And, okay, so you do it in such a way that each of these parts has no rainbow triangle. Okay. And then the colors between these different parts are very well structured. So between any two of these parts, the edges are actually monochromatic. So say between V1 and V2, maybe all the edges are yellow. Okay. And then the final condition is that the number of colors that are used in these external edges is at most 2. Okay. So maybe between V1 and VT, there's like green that appears, right? But yellow and green are the only colors that appear in these external edges, right? So this partition certifies that the graph is rainbow triangle free, because, you know, if you're a triangle that lives inside a part, you won't be rainbow because each of these does not have a rainbow triangle. If you go like between two parts, you won't be rainbow because you'll have 2 yellow edges, right? And then if you use 3 external edges, you won't be rainbow because there's only 2 colors that appears amongst the external edges, right? And T is at least 2.
Oh, okay.
This
So
one,
it's
right?
say even T1 is 3.
Yeah. So this is actually a decomposition theorem, right? Because you can reapply the structure theorem inside each one of these parts, right? So for example, in the base case where only 2 colors appears, you can take each of these parts to be like a single vertex. Okay, so this is Gallai's theorem, and so okay, I might not have time, but we basically prove a similar theorem for projective geometries, right? So we completely characterize all the triangle-free colorings for projective geometry. We know exactly what they look like, and then we can actually derive the our conjecture from the structure theorem. So let me show you maybe how that works for graphs, at least, so you get some inspiration. I can try. Let me erase this, I guess. I'll keep that up.
So this works with any number of colors.
Any number of colors, yes, yes. Any number of colors. I didn't know about this theorem before this project, but I think it's quite nice.
And you're not saying that V1 is complete to V2, right?
Well, this is, yeah, it is, because this is a coloring
I
of
see,
the,
I see. Yeah, it's complete.
yeah. So, right, so this theorem of Gallai can be used to prove the multicolored Erdős-Hajnal conjecture for rainbow triangles. I'll show you how to do that. And then our proof kind of just mimics, I don't think I'll have time to even state our structure theorem in the proof, but it's going to be analogous to what I do for graphs. So, lemma. So this approach, so this is a lemma of Fox, Rishvan and Pak. Right, so for every 3 coloring of the edges of the complete graph, there is an edge partition of Kn into 3 2-colored subgraphs. G1, G2, and G3, each of which is a cograph. Okay. So if you take like a rainbow triangle free coloring of Kn with 3 colors, you can partition those edges into 3 subgraphs, each of which, so like say a red-blue subgraph, a red-yellow subgraph, and a yellow-blue subgraph, such that each of these is a cograph. So remember, a cograph is something without this induced path with 3 edges.
So is there a precondition on your 3 coloring?
Yeah, so there is, right? So with no rainbow triangle. Sorry, thank you. Yeah, so these are sometimes just called Gallai colorings because of Gallai's theorem there. So this has a pretty nice proof. So we just go by induction on n, right? So all we do is just apply this structure theorem. So we have these blobs here. And the structure theorem says each of our blobs has no rainbow triangle. So this means that by induction, I can partition all the edges inside each part into something that's, let's say, the edges. So there's going to be a part that's red-yellow, there's going to be a part that's red-green, and then there's going to be a part that's yellow-green, let's say. Right? Where each of these is a cograph, right? And I know that amongst the external edges, there is some color that's missing. So let's say, let's suppose, I'll do it here. So suppose green is missing among the external edges. Right. So then now all I need to do is to somehow combine all of these cographs into a decomposition of like all the edges of the complete graph. So I need to include the edges that go between these parts. So it's all pretty simple, right? So so for example, this blob also has like this decomposition, yellow, green, red, green, or sorry, red, green, and red, yellow, right? And I know that the edges between this is either like red or yellow, right? So maybe let's say it's red, right? So this means that I can just take the join, right, of this guy and this guy, the red-yellow part. So amongst the external edges, only red and yellow occur, so I can merge this red-yellow subgraph with this red-yellow subgraph, right? This will still be a cograph because the join of 2 cographs is another cograph. And then with these guys, I can just take the disjoint union, right? So for the green things that occur, there are no green edges that go between these parts. So I take the disjoint union of all these guys and the disjoint union of all these guys. So that gives me 3 cographs which will partition all the edges of the big graph. Right? So that's the proof. Okay. Okay. So with this proof, we can prove this theorem for rainbow triangles. So okay. So That's
I missed the last one. So when you so G for instance G1 is red, red, yellow, subgraph.
yeah. So maybe think of this as a small G1, and this is a small G2, and this is like a small G3,
Yes.
right? So I know that between any two parts, it's either going to be red or it's going to be yellow. So I'll use, in either case, I can merge this G1 with this G1, even if this was yellow, right? Because it's not going to be green between these guys, right? And then these guys, I take the disjoint union of all the small G2s, and I take the disjoint union of all the small G3s. So that will be a partition of all the edges, because the G1s will eat up all of the edges between these parts.
Oh, I see. So you take all the red edges between them, put it into G1 in this case?
Yeah, I just take the join of, so I have all the small G1s. I can assume that it's a spanning subgraph because I just add isolated vertices that will,
It's an edge partition.
and then I just take all of them and all the edges in between. Is it okay? Okay, so then with this lemma we can prove this multicolored Erdős-Hajnal for rainbow triangles. So let me do that proof. So the bound that we'll prove will be like I guess like an n to the 1/3. We'll get a n to the 1/3 bound. Okay, so how do we do it? Let's look inside G1. Right, so I have G1. Right. And G1, as I said, we can assume that this is like a spanning subgraph, so there's like n vertices. Right? Okay, so now I just ask, okay, does G1 have a large clique? Right? So, so if omega of G1 is at least n to the 1/3, we're done. Right? Because remember, G1 only has like red and yellow, so it's missing green. That'll be good, right? So the key property that I'm using is that these are cographs. In particular, they're perfect, right? So for perfect graphs satisfy that if I multiply like omega by alpha, this is always at least the number of vertices of the graph. Right? So for perfect graphs. Okay, so if this fails, this means that G1 has a large independent set, right? So it has an independent set of size like n to the 2/3, right? So, so alpha of G1 is at least n to the 2/3, right? So let's take a large independent set X of size of X is at least n to the 2/3, right? And then now I just ask, well, what do G2 and G3 do inside this set X, right? So, so let's first do it for G2, right? So, so again, if omega of say G2 of X is at least n to the 1/3, we're done. Right? So I look at what G2 does on this set of vertices. If there's a clique, then I'm finished, right? So again, I use this perfect graph inequality. So this means that, so this alpha of G2 of X is at least n to the 1/3, right? So now there's a stable set inside X in this graph, Y, that's pretty large. But this y now is a clique in the third graph, right? Because remember, this is a partition of all the edges, right? So that's quite a, I think, acute proof. Okay. It turns out that the right answer is this n to the 1/3 times a log squared, but that takes a lot more work. So what they actually prove is that n to the 1/3 times log squared n you can get, and that is tight, actually. Okay. Okay, so so the way we do like the rainbow triangle case is completely analogous to this. We prove a Gallai's theorem for projective geometries, and we just pretty much do a similar thing. I wanted to do kind of okay, so let's maybe I don't have time. But I wanted to mention that these two cases are much harder, and the only way we kind of know how to prove them is by like a very like recent result in additive combinatorics that we just use as a black box. So this does all of the heavy lifting for us. Maybe I don't have time to state what to state what that result is, but very loosely it says that if you take any set of points, say that I'm looking at vectors, say binary vectors of dimension n, right? So any set of points is either going to have a large dimensional subspace, like sitting inside there, or if you take like the sum of that set, so this is a result of additive combinatorics, if you take x plus x, that's going to have a large independent set, right? So there's a notion of independent set in cliques for projective geometries. That's what that's the result that we use. But anyway, you can ask me offline how to do it. So these are kind of completely different methods, actually, even just for this triangle. Right? So this uses some really heavy machinery from additive combinatorics. This uses some exact structure theorem for these rainbow triangle colorings. So maybe I'll just stop.
Thank you. Any questions? Yeah.
Yes, so in the beginning you talked about Erdős-Hajnal conjecture about this cliques and independent sets. So let's say for H is C5, there is always, you said there is already a proof that there exists a homogeneous set of n to the power delta. So the proof shows the existence, or do they also tell you how to build it in, say, polynomial or something like that?
I don't know exactly, but a lot of that stuff is constructive. Like they want to, okay, yeah, say if you want to use the regularity lemma, then you want some algorithmic versions of the regularity lemma. So, okay, I'm not sure, probably the best is to ask those guys, but yeah, maybe you can find it, actually, but
how strong are the quantitative bounds you get in over F2?
yeah, so what we prove, say, for like the rainbow triangle case is completely tight. So we do verify like the stronger conjecture for the rainbow triangle. So you just need, you can take delta, yeah, you can take delta equals 1 as we conjecture, and I think C to be 1/3, so you get n over 3.
And that's the 1/3 is also tight.
That's tight. So this is sort of completely solved. For these guys, the result from additive combinatorics gives us n to the 1/7. But okay, if you believe the bold conjecture, then it should be linear. So there are strengthenings of that result that we use. That those results could even be linear, but I don't think anyone knows how to prove that.
So also quite related question. So is then one sort is independent from the choice of Q, or only Q is 2K?
Yeah, so this is for Q equals 2. Like our structure theorem is for all Q, actually. So like we can characterize all the rainbow triangle free colorings, even for any finite field. But there's a difference, I guess, because like when Q is not equal to 2, like the notion of a line and a triangle are different, actually, right? So you can't really apply. Yeah, like, but when Q equals 2, like a line is a triangle, so it happens to be a projective geometry. Yeah.
So then you mentioned that for the monochromatic one, your bound is n to the 1.
Yeah, both of these will be n to the
1/7.
n to the 1.
For every Q.
No, this is just for Q equals 2. This
Only
is still,
two.
yeah, because this, like, this is only a projective geometry when Q is equal to 2, actually, right? So, yeah, and then the C we don't really know, like, because the C comes from their proof, and it's kind of unclear, like, what that constant is.
Other question?
Do you get to obtain some projective geometry analog of co-graphs?
Yeah, that's a good question, I guess. So it would be nice to get, like, again, at least some infinite class of, yeah, like, at least some kind of colorings, that infinite class of colorings. We have some more, so using some theorems of Peter and his student, there are some more cases we know, actually, than just these 3. But it would be nice to, yeah, to get more.
So do we know actually how, like, co-graph on project geometry?
Yeah,
looks
yeah.
like?
So it should be something like you take a 2-color version where, yeah, like that, maybe the red points induce a co-graph, whatever that means. Yeah, that.
Okay.
Yeah.
But in your result, you didn't get the precise characterization of co-graph analog.
No.
So how come here you get n cube root and you get n? So
Yeah,
something
that's
must have been
just
different.
what I was saying, that like these I think are nicer questions sometimes in the geometric world. So our proof is cleaner and it's tight actually, whereas they actually had to do a lot of work and this log squared factor like creeps in. So somehow the geometric world is a bit easier. So like, yeah, people should work on it. So yeah, like so I should say like the result like that we use from additive combinatorics is by I guess Kelley and Meka. Like it's this right bounds on sets of numbers that don't contain like 3-term arithmetic progression. But they did a lot, so we just specialize what they did into our setting, and it gives this n to the 1/7. But they really prove a lot more than this n to the 1/7.
Any more questions? If not, let's take the speaker.